So the slide is called example of the null spaces. So here's the first example. It's the example which is called orthogonal complement subspaces. It's something we introduced a few weeks ago, and I will remind you what that is. Thank you. That's how we introduced the orthogonal complement subspace. This is just a blast from the past. If I fix a vector with n components in Rn, this symbol, I used it to denote the orthogonal complement subspace, if you remember, and that's how I defined that. It was all of the vectors x, again, n component vectors from Rn, such that the dot product between a and x is 0, and here's the expansion for the dot product. This is the expanded version of the definition of the orthogonal complement subspace we studied with you quite extensively a few weeks ago. Now, I claim we proved that this is a subspace directly with the subspace theorem. But this time I claim that this object can be seen as a null space of the specially crafted linear operator. Here's my crafting. If I take the linear map between Rn and R, and R such that this T takes an x vector, this x vector, to a dot product, which is a number, then, well, that's for any x, then this map will be linear map. And if you believe this, I will prove this in a second, but if you believe that this is a linear map, then this symbol is exactly the null space of this linear map. That's exactly the set of vectors which are taken to 0 vector under the action of such a map. It's a null space by definition from the previous slide. So if I prove that this is a linear map, that will be enough evidence to conclude that this one is a subspace. So it's alternative proof of the same fact, even simpler proof. So why do I know that T is a linear map? Why do I know that? Well, I can link again, I'm not going to do it directly. I'm not going to check the two properties of a linear map. Instead, I will link my T to some other linear map we have studied already on Tuesday. Here's my linkage. I claim that my map can alternatively be seen as a matrix product, AX, where the capital A matrix is simply my A vector transposed. So it's the matrix of one row and n columns, and it is filled with the components of the vector A. It's the matrix of one row and n columns. And we proved with you 2 days ago that any map of this type, I call them matrix type linear maps, is a linear map. You see how much time you can save by doing the proper referencing and structuring your approach. I haven't proved much in my presentation. I just make the linkage to facts we established already with you before. It's an art to be able to do this kind of things. It's a very disguised compliment to myself, you know. Well, I'm hoping some of you will pick up the elements of that art and impress me in return also when you do your tests or exams. Anyway, that's one example. The other example of the subspaces, which can also be fit into the same scheme, is this one. The second example on this slide. We also established with you quite rigorously that if you take the intersection of the orthogonal complement subspaces, so if you take something like this, you take orthogonal subspace as above, and you intersect it with another orthogonal subspace with respect to some other vector B. If you take intersections, that also be a subspace. We have proved that. There were a few tutorial questions actually in relation to this problem. So here's my expansion for this symbol. So it's a vectors from Rn, like this, which vanish 2 dot products at the same time with A and with B. So yeah, here we go. We have proved that this development of this example with one vector, when you take the intersection, it is also a subspace. I can make this example fit into the null space scheme as well. I just have to craft again this linear operator properly. How am I going to do that? That's how I'm going to do it. If my B vector has components B1 P2 Bn, if my B vector with such components, all I do is this. I take a linear operator T, which takes n-dimensional vectors into two-dimensional vectors this time, and which will be matrix type linear map with this matrix. Look at this. My A matrix will be the matrix of this type. First row will be the components of A vector, and second row will be the components of B vector. Here we go. If I take such a map, if you imagine what this map does on the vector x, what it does, it takes this n-dimensional vector, it returns two-dimensional vector, so it will be two components in that vector. First component will be the dot product of the first row of this matrix and the column here, which is this regular dot product. And the second component of this vector here will be the dot product of the second row here and the column here, which is the second dot product here. So when you require that T, when you require something like this for this map, you require that the first and the second component simultaneously is 0. That is exactly this condition. And so you see my space fit really nicely into my general scheme of the linear matrix linear map with this specially crafted linear transformation, linear map. And that's why now I can say that S is a null space of this new linear transformation. And that's why S is subspace, even though before we proved it differently.